In this section, we're going to talk about alternating series, what an alternating series is, and we're going to look at the alternating series test to determine whether an alternating series converges or diverges. We're also going to look at the idea of absolute versus conditional convergence for series. So we'll start with what is an alternating series. An alternating series is just one where each term has an alternate sign. So either the first term is positive, the second term negative, and so on, or the first term is negative, the second term positive, and so on. So the sign has to change in between terms. The alternating series test says that if we take those terms in the alternating series, just the terms and not the signs, the limit as n approaches infinity of a sub n has to equal 0, so you have to check for that. And then you have to check that all the terms, again, not looking at the sign, but the terms themselves as you go through the series are non-increasing. So that means that they either have to be decreasing or they can stay the same. They can all be equal to each other, but they have to be non-increasing. So to use the alternating series test to say whether an alternating series converges or not, when you justify that, you will have to say that it is an alternating series before you can use the test. And then you'll have to show those other two conditions. And we're going to look at different ways to show that the a sub k are non-increasing. But you'll always state that you have an alternating series. You'll show this condition, the limit as n approaches infinity of a sub n equals 0. And then you'll use one of the three tests I'm going to show you to show that the a sub k are non-increasing. So let's start with this example here. So this is an alternating harmonic series. You should recognize this as being very close to the harmonic series we know as just the k equals 0 to infinity of 1 over k. And we know that that diverges. But this one is an alternating harmonic series. So we have that it's an alternating series. We have that first condition. The second condition is we have to show that the limit as n approaches infinity of a sub n equals 0. So a sub n, in this case, we're ignoring this part of it. So if they were all positive, they're just 1 over n. So we're looking at the limit as n approaches infinity of 1 over n, and that is 0. So this series meets the second condition of the alternating series test. And then we're going to use something called the algebraic difference test to show that the series is non-increasing. Basically, the algebraic difference test shows that if you take one term in the series and you subtract the term before it, that you are going to get a number that is less than 0. Or in other words, that term is a sub n plus 1 is less than a sub n. That the next term is smaller than the term before it, is what the algebraic difference test says. So in this case, our a sub n plus 1 is equal to 1 over n plus 1. And if I were to subtract those, I would get a number that is less than 0. I get a negative answer. And so then it passes that. So that determines that it is non-increasing. Since this meets all the conditions of the alternating series test, this series converges. All right, on this alternating series, our a sub n first of all, we know it's an alternating series because of this -1 to the k. So that means when k equals 1, this will be a negative term, but when k equals 2, this will be a positive term, and so on. So that makes it an alternating series. So now we can use the conditions for the alternating series. So a sub n is 2n squared plus 9 over n squared plus 1. Well, the limit as n approaches infinity of that is equal to 2. Since it's not 0, we can stop there and say that the series diverges. So we already looked at the algebraic difference test, showing that if this difference between a term and the term before it is less than 0, that makes it decreasing. If it's equal to 0, that makes it non-increasing. So it can be less than or equal to 0 for all of the terms. So n has to be greater than or equal to 1 so that we can at least have a sub 2 and a sub 1. The ratio test takes a term and makes a ratio of that and the term before it. And if that ratio is less than 1, then that means that this number is smaller than this number and it is a decreasing. Those are decreasing terms. And if it's equal to 1, then again it means they're the same. So it's non-increasing. And then the derivative of a related function. So you take the function in terms of n and you make it equal to some f of x function. And you show that the derivative of that f of x function is less than or equal to 0. So if the derivative of that function is less than or equal to 0, that makes it a non-increasing function. We learned that way back the beginning of calculus of when we were learning about derivatives, that derivatives of functions, if they were negative, that meant the function was decreasing. And if they equaled 0, they were constant, so the function is not increasing. So that's another test that you can do. And again, it just kind of takes practice to see which one of these tests is going to be easier to use. So in this example here, we have the factorial. Anytime you have the factorial, the ratio test is going to be easier, and I'll show you why. So here our a sub n is 1 over 2n factorial. So the limit as n approaches infinity of 1 over 2n factorial is equal to 0. Okay, again, we have 1 over bigger and bigger number, so that limit's going to be 0. So it's an alternating series because of this -1 to the k. It meets this condition of the alternating series test, so now we need to check the non-decreasing condition. So in the ratio test, we're going to take 1 over 2 times n plus 1 factorial. So that's our a sub n plus 1 term over the a sub n term. So if we flip, that gives us, if we multiply by the reciprocal of the bottom, that gives us 2n factorial over, and then I'm going to multiply that 2 through here to get 2n plus 2 factorial. This I can rewrite as 2 to the n factorial, because all that this is missing from this is 2 to the n plus 1 and 2 to the n plus 2. Otherwise, these have the exact same terms in them, because remember, a factorial just means add. It's like a series. It means to add all those together. So 2 to the n factorial is only missing these two terms. And I'm sorry, it's not adding, it's multiplying. So if we go ahead and multiply by those two terms, then these are the same thing. But what that allows us to do is this is 1. These are the exact same number. And so that's equal to 1 over 2 to the n plus 1 over 2 to the n plus 2. And that is less than 1, no matter what n's I plug in there. I'm going to get a number bigger than 1 down here. So that number is less than 1, and therefore it's non-increasing and this converges. So we've seen an example of the algebraic test for non-increasing, and now we've seen an example of the ratio test for non-increasing. Now, so far we've just been determining whether or not the series converges or diverges. But we don't really, if it converges, we don't know what it converges to. So that's really hard to do, but sometimes we can use ways to estimate. Because remember, if it converges, that means that all the terms we're adding are getting smaller and smaller and smaller. So we're adding, as we get more terms, we're adding less and less and less. So the more terms we have, the closer we get to the actual sum. So if I want to know what the sum is with an error less than or equal to 0.001, that would be meaning that I have a number and anything I add after that is going to be less than that number. And so I'm that close to the actual sum. So to do that, we need to find which term is going to be less than this number. And that's this term right here. 1 over 8 factorial is the first term that is less than 0.0001. All the terms before that are more than that. So now I can just estimate the sum. Instead of going to infinity, I'm just going to add the first 4 terms. So that would be 0 to 3. And so when we do that, when we add those first 4 terms, putting that in your calculator, you get approximately 0.540. And so we can say that this series converges and the sum is about that, and our error is less than 0.001. Less than or equal to. Okay, now we're going to talk about this idea of absolute convergence versus conditional convergence. It's important to know that determining whether if you determine that a series is absolutely convergent, that means that that series is convergent. But it doesn't mean that if a series is convergent, that it's absolutely convergent. So that's important. Okay, absolutely means that it has to be convergent. But just because it's convergent, it could be conditionally convergent, and therefore it's not absolutely convergent. So hopefully that makes sense to you. So determining whether a series is absolutely convergent, if we take the absolute value of all the terms, so whether it's an alternating series or we just have some positive values and some negative values, or even if they're all the same, if we look at the absolute value of all of those terms and the series that includes the absolute values of all those terms, if that series is convergent, then we know that the series we're looking at is also convergent. and it's absolutely convergent. And if it's absolutely convergent, then we can say that that series converges. So in this example here, this is very much like a geometric series, except for the fact that we have some positive signs, some negative signs, and it's not an alternating series because they don't alternate every other one. So we can't use an alternating series test, but we can check to see if the absolute value of that series converges. And if it does, then this series has to converge too. So if we use the absolute values of all of those, then we get this series. We get k equals 1 to infinity. And then it's always 1/2 to the k minus 1 power. Because when I plug in 1 here, that's how I get that positive 1. When I plug in 2 here, that's how I get 2 to the 1 power, 2 to the 2 power, 2 to the 3rd power, and so on. So remember, I'm ignoring the signs right now. I want them all to be positive. And so this is this series if all of these are positive. Well, this is a geometric series. And since the absolute value of r is less than 1, this series converges. So by the absolute convergence test, our original series also converges. Okay, on this one, we have to do a little bit more finagling here. So we want to look at, again, we've got a series where they're all positive, but it's something I don't know how to determine if it converges. It doesn't match any of the series that I know, and so I'm going to have to do a little bit more with this. Also, the different terms in here. Some of them are positive and some of them are negative. As k gets bigger, I can get negative terms, negative answers for sine, and positive answers for sine. So it isn't any of the special ones that we know. We can't say it's a geometric series or a harmonic series or whatever, the way that it is right now. But if we look at the absolute value of it, and we know that the absolute value of sine of n has to be less than or equal to 1. We know that about sine. If we take the sine of any number, we know we're always going to get a number that's between -1 and 1, or equal to -1 and 1. And then so if we take the absolute value of that, we get this, that it's going to be less than or equal to 1. That means that the absolute value of sine of n over n squared has to be less than or equal to 1 over n squared. Because n squared is always going to be positive. So now we're going to use the comparison test, because 1 over k squared, which is like 1 over n squared, this series is a p series where p is greater than 1. So this series converges. That means that the original absolute value series also converges. So I use the comparison test for the absolute value test, and because it absolutely converges, then this original function our series converges. So that was a little more complicated because not only did we have to use the absolute convergence test, but while we were doing the absolute convergence test, we also, to determine if that series converged or not, we had to use a comparison test. So everything that we've looked at so far either diverged or had absolute convergence. And again, remember, if a series is absolutely convergent, then it converges. But just because a series converges doesn't mean it's absolutely convergent. It could be conditionally convergent. So series that converge and are not absolutely convergent, that don't pass the absolute convergence tests, but we still know they converge, those are conditionally convergent. So in this particular problem, what we're looking for is at different values for P, is this series going to be absolutely convergent, conditionally convergent, or divergent? So first we're going to do the absolute convergent test and see, are there any values of P where this series is absolutely convergent? So if we use the absolute value of this, that's going to be the same as 1 over k to the p. So it's a p series. And in a p series, it converges if p is greater than 1, but diverges if p is less than or equal to 1. So this series converges if p is greater than 1 and diverges if p is less than equal to 1. Well, because it converges if p is greater than 1, then we know this series converges if p is greater than 1. But we don't know what happens if p is less than or equal to 1. So for that part, we're going to use the alternating series test. Again, this is an alternating series because of this. That -1 means that for each k, we're going to alternate between negatives and positives. So it's an alternating series test. So what we want to do is we want to look at the limit as a sub n approaches, or as n approaches infinity of a sub n. A sub n is 1 over n to the p. And remember, we're looking at values where p is less than or equal to 1. So this is 0 if p equals, if p is between 0 and 1. But if p is less than or is equal to 0, then this equals 1. So if p is equal to 0, that's 1, so I have 1 over 1. If p is between 0 and 1, so p is positive number, then this, we're going to have 1 over a bigger number, and so that's 0. And then if p is less than 0, this goes to infinity. That limit is infinity. Well, we know by any tests, if the limit is infinity, then that diverges. So here, if we know it diverges if p is less than 0. So now we're just not sure about what happens here, whether it's conditionally convergent or whether it diverges. So we have the first condition met, or it's equal, the limit is equal to 0, but now we have to check to see if it's none. increasing. And here's where we get to that third test. This is a good one for the derivative test. So we're going to say that f of x is 1 over x to the p. So then that makes f prime of x, using the power rule, if we call this x to the negative p and we use the power rule, we get negative p over x to the p plus 1. Well, that is less than 0. So the derivative test says if the derivative of that function is less than 0, then that function is decreasing or non-increasing, which makes this series non-increasing, which means that it is conditionally convergent if p is between 0 and less than or equal to 1. So this is a good little chart to help you to decide whether a series converges or diverges. So if this series converges, then our series is absolutely convergent if that the absolute value converges. This series is conditionally convergent if we figure out that the series converges, but the absolute value of it diverges. And if neither of those are true, then then we would say that this diverges. So if we use some other test and figure out that a series diverges, we're done. If we figure out a series converges, but we want to know if it's absolutely or conditionally convergent, we have to see if it passes the absolute convergence test. So that's what we did. We did the absolute convergence test for p is greater than 1. But since we knew that if it was less than or equal to 1, it wasn't absolutely convergent, then we had to see if it was convergent in that area. And it was only between 0 and 1, so it was conditionally convergent. And because it didn't converge at all, it was divergent. If it was 0, then we went straight to here. These are just some properties about absolutely convergent and conditionally convergent series that you should read through and know. So if a series is absolutely convergent, you can rearrange the terms because you're adding them. And that new series is also absolutely convergent. And they'll have the same sum. Rearranging the terms doesn't change the sum of the series or whether or not it's convergent. If you have two series that are absolutely convergent, then if you add those series together, they will also be absolutely convergent. Here, if I have two series that are absolutely convergent, and then I multiply the terms in those series together and make a new series, that series will also be absolutely convergent. And the sum of that series will equal the product of the sums of these two series individually. If a series is absolutely convergent, then if I make that series and I just take the positive terms out of it, and that converges, that will also converge. And if I just take the negative terms out of it, that will also converge. Series that are conditionally convergent, however, if you just take the positive terms out of it, that will diverge, or if you just take the negative terms out of it, that will also diverge. So the series with both the positive and negative may converge under certain conditions, but if you just take the positive or just take the negative out, those individual series will be divergent. And if a series is conditionally convergent and you rearrange the terms, you can rearrange it to form a new series that converges to any sum you want. Even you can rearrange it to form a divergent series. So that one, because of the different signs in it, it's possible to get a divergent series because you've rearranged things if it's conditionally convergent. If it's absolutely convergent, then that's not possible.